Okay, so now let's begin the transformer from the beginning. So transformer can be defined as the static electric machine. Okay, it does not have the moving parts, so it is the static electric machine, and it is based on the Faraday's electromagnetic induction, and there is the relative motion between the electric field and magnetic field to produce the EMF. Okay, so here the flux is moving, so you can say that the flux part is moving and the current is supplied and relative motion is there, so EMF is produced using the formula E is equal to minus dlv. Okay, so this is the construction of the transformer. So the middle portion is the core of the transformer, and it is made up of the ferromagnetic materials or permanent magnetic material or any other material in which the permeability is very high. Okay, and N1 and N2 are the number of turns of the primary winding and the secondary winding. Primary side is connected to the source and secondary side is connected to the load. V1 is the applied voltage, E1 is the EMF produced in the primary side. It is also called back EMF. It opposes the applied voltage. Okay, and E2 and V2, since E1 opposes the back EMF, so the if we are representing by the phasor, then E1 is here, so V1 is here, and this E1 and E2 are in phase, so again E2 is here, and E2 and V2 is also in phase, so again V2 is here. Okay, and flux is here. Okay, so EMF is lagging the applied flux by 90 degrees. We will derive this equation later. Okay, so what happens here, that these are tightly coupled. Okay, the windings are tightly coupled, and to reduce the eddy current losses, and alternating voltage is supplied which causes the alternating flux to flow. This flux flows on the mean path of the transformer core in the center. Although this core is also made up of many thin lamination, it is not a single piece. It is made up of many laminations which are joined together by bolting. Okay, so alternating supply causes the alternating current to flow in the primary winding. Okay, and since flux is directly proportional to current, so alternating flux is produced or starts flowing in the core of the transformer. So this alternating flux is linked with the secondary winding, and again there is a relative motion, and when there is a relative motion, the EMF of the secondary side is produced, and if the load is connected, then the voltage V2 is developed across the secondary side. If there are some drops, it's good enough. If it is not still, then the E2 will be equal to V2. Okay, so since the back EMF opposes the applied voltage and also the primary current. Okay, so the electromagnetic energy conversion takes place whenever there is some opposing force. Okay, so this is the universal factor, and alternating flux produces the alternating voltage in the secondary side, and since the DC system does not have the alternating flux, so transformer works only on the AC system, and also the continuous passage of current will heat up the transformer and it will burn. Okay, so next is our EMF equation calculation. So EMF is nothing but the minus d phi by dt, you know, but if we take the magnitude, okay, then it becomes n d phi by dt. So this is our sinusoidal flux. So if you take the d phi or the change in flux at any 2 points in this curve and divide by the time taken for that change, we will get the EMF. And if n are the number of turns, then it becomes n d phi by dt. For example, in this present case, we have taken phi m here, okay, and minus phi m here. So phi m minus phi m becomes 2 phi m, and it is divided by, if t is the full time period, then t is equal to 1 by f is the frequency. So half time is 1 upon 2f. So 1 upon 2f is there, and it results in the EMF, which is the average EMF. Okay, so this is the average EMF. It is true for each and every point. Let's consider one more point here. Suppose that this is our flux. Okay, yeah, ऐसे लेगा. So if it is phi m here and 0 here, so phi m minus 0 becomes phi m, and this is the 1/4. Okay, that is t by 4. T by 4 means 1 upon 4f. So if 1 up phi m upon 1 upon 4f, what it become, it will give the same result. Okay, this is the phi m, this is 1 by 4f. So this 4f goes up, so we will get phi m 4f, and if the n are the number of turns, then it becomes n. So this is the average value, and since it is a sinusoidal quantity, the RMS value can be calculated by multiplying this average value by 1.11 or form factor. So we will get the RMS value as 4.4 phi mfn. Okay, if this is the EMF of the primary side, then it becomes E1, it becomes N1. If it is E2, it becomes N2. Okay, similarly, we can derive this ERMS using same single phase concept. This is just the repetition. Okay, sin theta, em sin theta is 8, em square sin square theta, d square d theta 0 to pi से integrate कीजिए, 1 by pi से divide कीजिए and take the root. We will get the RMS and we will get the average, and if we divide it, it becomes form factor of 1.1. Okay, so in this way we can calculate the EMF of the transformer. Now let's move further. So there are few small concepts of turns ratio. So turns ratio is nothing but the ratio of the primary turns to the secondary turns. It is n1 upon n2, and it is also denoted by np upon ns. Okay, so if t is equal to 1, then it becomes 1:1 transformer, and if the secondary turns are more than primary, then it becomes step up transformer, and vice versa. And voltage transformation ratio is the ratio of the voltages of the secondary side to the primary side. So V2 upon V1 becomes K, and they are directly proportional to EMF. So E2 upon E1, and EMF is dependent upon the number of turns, as we have seen here as well. So E2 upon E1 or V2 upon V1 is dependent upon the ratio of the number of turns. and since the rating of the transformer is same, v1 of v1 I1 is equal to v2 I2, so we can calculate the transformation ratio with respect to this current ratio. Okay, so next topic is our ideal two winding transformer. What? So transformer is static device and it is having very good efficiency. Okay, so the ideal transformer should be lossless system, or it should have the 100% efficiency,